I welcome you all for this NPTEL lecture on earthquake resistant design of foundation. Today we are going to talk 36th lecture of this course, which is on soil pile introduction. And this lecture is a part of the 5th module of the course, which is on SSI, that is soil strength introduction. So you could see in this slide that this is lecture number 36, and we are under 5th module of the course, that is SSI 4D foundations. And within these modules, there were 6 chapters. 5 chapters we have already discussed. Today we are going to talk the last chapter of this module, that is on soil pile introduction. And within this chapter, today we are going to cover these topics. First one, recent advances in soil introduction. Then we are going to talk about SPSI, that is soil pile structure introduction using Kelvin elements of boundary. And finally, the evaluation of the soil parameters in laboratory. So let's discuss what are the recent advances in SSI. In fact, significant advancement has been made in this area in last 3 decades. And this was possible because there was quite much advancement in the computer technology. And it is possible to model and analyze SSI problems more rigorously. Most of these advances are on 2 major and very important issues. What are those issues? First issue, the soil is an unbounded domain. However, still its precise modeling is possible. The second, the behavior of soil during strong excitation is highly nonlinear, and for saturated loose ends, even the liquefaction may occur. So first thing is the modeling of the boundary, and second is related to how to consider the nonlinearity in the analysis. The first one, the modeling of the boundary, we will discuss in detail. However, till today, no commercial softwares such as SASI, Flux, Classy, Flag3, Dyna, Plexus adequately deals with these important issues. And for these important issues, our research group is working. And the research group, which includes my PhD students also, and particularly let me mention the Mr. Imani, Mr. Shakar, Mr. Saeed, they work extensively in the area of soil introduction and soil pile introduction. So these are the few of the work which is listed here. First one, the Maheshwari 1997 is the work of my own PhD, where the material and geometrical nonlinearity in the theory of which was proposed by Engg and Kozol in 1982, pile dynamics, which was basically for linear analysis, has been introduced. Then in 2003, which was a postdoctorate work, what has been used? The Kelvin elements has been used to model the boundary and this HS whole model to deal with nonlinearity. Then Imani, the first PhD student in 2008, carried out nonlinear SSI analysis using what is called CIFECM, that is consistent infinitesimal finite element cell method for boundary, and use hybrid methods. Then later in 2009, the Sarkar considered liquefaction for SSI analysis, and recently in 2014, the Saeed modeled the boundary using SPFM and nonlinearity of soil using HS, his soil model. So these were the some of the that advancement made in this area of soil introduction by our research group, and we will discuss some of them only, not all, because it is not possible and it is not required also, because we are dealing only for as a part of artificial design of structures. We need to see that how to model soil pile introduction, because pile foundation is one of the important issue which is required for the seismic loads. So coming to here, one of the important issue or where the advancement has been made in SSI analysis are related to modeling of boundary. Then there are, when you have you go for the modeling of boundary, then there could be approximate model or there could be rigorous boundaries. So in this case, the approximate boundaries has been used, and these boundaries, approximate boundaries, are local in space and time. So these boundaries can be classified under this category: the element boundaries, the viscous boundary, Kelvin elements, transient transmitting boundaries, and infinite elements. So the elementary boundary and viscous boundaries we have discussed in the last lecture, where we talk about ground response analysis. and one of the boundary was consistent boundary. So in the consistent boundary, Kelvin elements is also one of the consistent boundary, which consists of spring and dashboards. So using the Kelvin elements, some of the work has been done in 2003, as mentioned in this report, which is Maheshwari 2003 used, and we are going to discuss some of the results. First of all, modeling and some of the results also. So let's see how to do Kelvin elements. So what we are going to discuss in next few slides, that is soil pile structure interaction using Kelvin elements and boundary. So using this one SPSI for structures which are supported on pile foundations. So what we have the problem of SSI, which is basically soil erosion interaction. This problem can be called in soil pile structure interaction, that is SPSI. And in this case, response of SPSI system will consist of what we call the kinematic interaction plus inertial interaction. What is Ki and inertial interaction? II, which we have already discussed in last in the second lecture of this module, that is 32nd lectures. For SPS system, that is soil pile structure system, there are two types of interaction effect. One is called soil pile interaction, means interaction between soil and pile. If you have a single pile, then it will be soil pile interaction. But in case if you have a pile group, then it will be called pile soil pile or group interaction. Then the second is foundation structure interaction. So both these types of interaction need to be required to be considered. That means interaction between soil and pile, and at the same time when your foundation, which consists of pile foundations, plus how it interacts with the structure. So these are important issues. Now, for the linear analysis, a methodology was developed, which has been published in a paper called Soil Dynamics and Earthquake Engineering in 2004. And this linear analysis, what is called successive coupling scheme, has been used. And why it has been used, let me tell you the background. You have this the pile foundations, and the top of the pile foundation you have a structure. Okay. Now, for and this, let's say we are assuming we have pile foundation. Piles are the end bearing piles are situated on the bedrock. Now, suppose we need to analyze this system. So one way that we analyze this system together, assuming that the structure and this foundation system, keeping them in together, and then we analyze the system. That is, so this is possible. But in that case, this will require a lot of computation, because the number of degrees will increase. So of course it is possible, but this work which I am presenting, this was done back in 2004, and how it can be easily dealt, that we are going to discuss. So what has been done here? The structure and the foundation systems are separated here. So that means one time you consider foundation subsystem, in another case you consider structure system, which consists of columns and frame structures. So what is done? And the time history analysis, the time of excitation has been divided into a small interval, where the interval is denoted t equal to delta t. Delta t is the small interval which has been considered. So at the first time step, what is done here? For the foundation subsystem, you apply the input motion, which is coming acceleration, which is coming the acceleration due to the earthquake load, which is applied here, and assuming only the foundation subsystem and there is no structure on top of it, then this is solved. In the first time step, it is assumed that there is no forces acting at the top of the column or base of the top of the piles here. There is no, at this top of the piles, these are the piles here. At the top of the piles, no inertial force is acting. So only input motion is applied, though no inertial force is acting. Then this system is solved. And once this system is solved, then what we find? We find this acceleration at the top of the piles, which is denoted U double dot T. This was input, this was output of the first system. Then this is inputted, and this input will lead to what is here. Input given to the base of this structure is U double dot G delta T, where UG is the acceleration at this level, which is the junction between the pile head and the base of the column. So acceleration here will be the same as the acceleration of the pile head. So input is given to the subsystem, and this subsystem is told to calculate the forces coming to do this acceleration at the pile heads. So by this analysis, we find out what are the forces which are acting at the pile head, that is FP delta D. Now in the second time step, this foundation subsystem, which is considered pile group, is subjected to earthquake excitation, which is usually acceleration at the second time step, as well as the forces at the pile heads, which was obtained in the system. Now we solve in the second time step and find out what are the acceleration acting at the pile head, and that acceleration will be input to this subsystem, and we keep going on. So this is a step-by-step analysis. And even if you go for the nonlinear analysis and you keep your time interval delta t small, then in that case, it is still possible to carry out the nonlinear analysis also. Here, one thing is here that we are continuously feeding from one subsystem to another subsystem, the input information, rather than solving one subsystem completely time-free and for another subsystem. And this scheme has been published, as mentioned here, in a journal publication, Soil Dynamics and Earthquake Engineering in 2004, and volume number 24, and these are the cases. Continue with that. So now let's discuss the applicability of this scheme, successive coupling scheme, which has been devised. And for that, what has been done? This has been applied for single pile as well as pile group. So what you have, in both cases, you have end bearing piles for single pile as well as pile group. And on the top of that, you have assumed a very simplified structure, which consists of a single column, and this dimension of that column is also given. And at the base, the dimension of the pile is given. So 0.5 meter is kind of a diameter of the pile, or because here square pile has been considered, so that is the dimension of that pile. Here you have the soil pile, and the pile is resting, it is assumed resting on the back. And the top of that structure is there. In both cases, the height of the structure is same. The dimension of the piles, diameter and height is same. Only the difference, you have considered single pile here, but here it is 2 by 2 pile group. That means 4 piles there. 2 piles you can see. When you consider the pile group, then spacing between the piles is important. Here, in this case, this diagram, this figure has been shown for the spacing ratio S by D equal to 5. That means where S is the center to center spacing between the piles. So you have a pile group here, and in the top of column also, rather than a single column, you have a group of columns also here. So now these are the two systems, which is one is for single pile system, another is 2 by 2 pile group systems, and both systems are subjected to earthquake excitation. Let's solve these both systems and find out what is the response of the single pile system or the response of pile group. So that has been shown in the next slide. So what is for the foundation subsystem? This is foundation subsystem you have. You have in this case 3-dimensional finite element models. This first case is shown for single pile and this is for pile group. These models are only for exclusive for foundation subsystem. That means without the structure column. So this has been shown here for this, and here what has been done, that the advantage of symmetry and anti-symmetry is taken. And once you have the advantage of symmetry and anti-symmetry, then the whole of your model is converted into a quarter model, not even half model. So you can analyze using quarter model only for the linear case. It cannot be used for the nonlinear case, number one. But at the same time, while using this quarter model or half model, one need to understand that how we are able to achieve this model. We are able to take the advantage of symmetry and anti-symmetry. And when we talk about this advantage of symmetry and anti-symmetry, not only your soil pile system, that means geometry should be symmetrical, but at the same time, your load applied should be also symmetrical. If your load is not symmetrical, in that case, we cannot use the system. So here it is assumed that geometry is regular. That means if you see in the plan for both the single pile as well as pile group, they are exactly symmetrical. So in both directions, in X and Y, this is 3-dimensional case. So this analysis is a 3-dimensional analysis. So you have, let's say, X direction this time, this is Z, and Y is perpendicular to the this screen. So that means it is symmetrical in all three directions, and the load applied is due to earthquake excitation that is also coming away from the down, which is also assumed symmetrical. So in that case, you can analyze this using what is called quarter model. So that means 1/4 of the full model is required to be considered. So when you go for the quarter model for this, so the pile will be only half in the single model case, and because 1/4 only. So this side you will have equivalent, this side you will have equivalent. So you have half this side and this side. So altogether it will be 1. So 1/4 model, only 1/4 quarter model of the pile is required only. Even half pile is not required. Then another issue is that when you cut down it, then you need to apply what is called this condition for excess of symmetry and antisymmetry, which we are going to discuss in the next slide. So here, when you talk about pile group, in case of pile group, in plan there was 2x2 pile group. So only 1/4 of the model is considered. So you get in this quarter model only one single pile. Okay. Now this single pile, this is applied, but only the thing that you can cut, you can consider one pile only instead of 4 piles. But in both directions, then you have excess of symmetry and antisymmetry. What is excess of symmetry and antisymmetry? Let's see here. So this is the plan and elevation for the pile group model. Well, that means for the second case, it has been shown here. So what do you see here? This is x direction in the plan, and this is y direction, while z is the vertical here. So what you have at the boundary of this model, Kelvin elements which consist of spring and dashboard has been used, number 1. Number 2, at the axis of symmetry, some rollers are attached, and these rollers are such that they permit the displacement along x direction, because you have a load is applied, input motion is applied as a in x direction. Here it is assumed that input motion consists of only the vertical loading shear waves. That means that this motion have that means only x component of the motion, but not y and z. So the input motion is applied only in x direction. In that case, the boundary condition of axis of symmetry is given here. That means this axis need to be fixed in x direction. Need to be fixed in y direction, though it is free in x direction when which load is applied. Another condition need to be applied, that this axis need to be restrained also in z direction. When we talk about the axis of antisymmetry on this side to convert this model into quarter model, then again you are keeping these nodes free to move in x direction, but these are restrained along y direction as well, and then free in z direction. So this was the boundary condition at axis of symmetry and antisymmetry, and at the boundary Kelvin elements as well. This was the top plan. In the front elevation also, you could see in the side spring dashboard, and only the thing that this triangle is showing confining pressure at different depths. So before you start your calculation, one need to consider the confining pressure, which is proportional to the height. So now coming to this was the modeling part. Continue with this modeling part. Let's discuss after this model what are the results. So when we talk about results, you have this study has been done very systematically, and in this study, the effect of SSI, that is solution interaction, has been studied under these headings, which is basically one objectives here to have the effect of frequency response. That means for harmonic excitation, how the system is behaving at different frequencies, or how the system is responding at different frequencies. So first of all, free field response is considered. Then the second, response of single pile, which will clarify soil pile interaction, has been considered. Then response of pile group, which will illustrate pile soil pile interaction, is considered. And finally, soil pile structure interaction has been also considered. That means on the top of soil pile system, the structure has been also placed in the last case. So let's see free field response. What is free field? You already know that free field is a case where you don't have any foundation, or you don't have any structure or inside the ground. So means, and it should be level ground. It should not be sloping ground. So in case of free field, there is nothing, no foundation, no piles inside the system. And in that case, when you apply the motion at the base of the bedrock, at the top of the bedrock, and it propagates through the medium, and when it reaches to the ground level, what happens to that depends very much on the frequency, as we discussed in the last lecture only, that is on ground response analysis. How this is affecting here for the soil pile system. So you could see in this case, in this slide. This slide is showing you effect of soil on free field response. Okay. On x-axis on the slide, the frequency variation is shown where omega is angular frequency of excitation. That means omega is dependent on your input motion. So then A naught is dimensionless frequency, which is defined as omega into D divided by Vs, where D is the thickness of the here. In this case, D has been the diameter of the pipe for this dimension, and Vs is shear velocity, which keep changing when you change the different types of soils, but in the same medium for it could be constant. So Vs is here. So let's assuming Vs is constant, D is constant. There is a variation in only omega. When you change the value of frequency omega, then naturally the value of A naught, dimensionless frequency, will also change. Now coming to y-axis, the free field response has been normalized with respect to the amplitude of the input motion. So you have input motion, which is this UG, which is the response at the ground, amplitude of the response at the ground, divided by the amplitude at the bedrock level. So this is also called transfer function, as we discussed in ground response analysis. And in this case, the effect of frequency has been shown. So what you could see in this graph, that the analysis has been carried out at discrete frequencies. So when the frequency is very low, like around 0.1 here, then you get at very low frequency, this ratio as almost 1 nearby. But as the frequency increases, this value of reaches and it reaches to a peak value, and after that it starts decreasing, continuously decreasing up to this point. And after this point, there is a little reverse bounce back. So what you can see that the maximum value of this normalized response is at the, it is at around 0.24. So that is the natural frequency of the system. Then another thing, as the frequency increases, this normalized free field response keep decreasing. Okay. So why it happens so? That because it is basically the effect of frequency, and this here damping is also considered. So damping affect the much the response amplitude is maximum, but less at other frequencies. So this was about free field response. Coming to the let's say for single pile. For single pile, you have soil pile interaction, and in this case again on x-axis you have dimensional frequency same, but on y-axis you have transfer function in the form of the response at pile head divided by the ground response UG. So in the last case you have UG by U naught, but here U itself is to divide or to normalize the transfer function, the value of amplitude at pile head. Again, the variation is that you could see that the effect of frequency is significant, but it is not so significant as was seen in the free field. And then what you have, these are the discrete points where the computation has been done. And so this solid line is showing that this solid line is that means continuously, and this is at discrete points. So what you could see again, this result is similar to whatever we have seen in the last case, but there is shifting of the frequency number 1, and at this point, this peak is quite high, and then it will start decreasing. So this shows the effect of frequency on transfer function or the response of the soil pile interaction. So this was the case when you have the single pile. But if you have the pile group, in that case the things are a little complicated. And in this case, a 2x2 pile group has been considered. And in this 2x2 pile group, what has been here? That means you have 4 piles, and one of the piles is you have the 4 files here, 2 by 2 file group, and we have models using what is called quarter model. So continue with this. What you have here is, let me come back to here in this. What I want to explain is S by D. S, what is S is center to center spacing between files, and D is the diameter of the file. So here, assuming diameter is a 0.5 meter, so you have this 2.5, so it will be 5, S by D equal to 5. But as you increase, then S is increased, and as a result, ratio S by D will also increase. So continue with this. So what you have here, or in this case, because you have spacing between files for file group, for file group, so spacing of the files is influence much these results. For example, what has been shown here is dynamic stiffness at different frequencies. And this dynamic stiffness, as you already know, we have also discussed earlier in our analysis also, that you have 2 parts because it is a imaginary number. So you have a real part and imaginary part. So the real part denotes spin and dash force, while the imaginary part denotes the damping system. What has been done? X-axis is same as before, that is normalized values of frequency. But on Y-axis, you have normalized with respect to static stiffness. So you have Kg, which is the group stiffness, divided by the N. This is the number of the files, and then you have this static stiffness. So static number of files divided by static stiffness. So this ratio is dimensionless. Same things for imaginary part. Here, this is CGS divided by NKS. So here you will have the values are increasing. Here, of course, this ratio will not be, because you are normalizing with stiffness only. So this ratio will not normalize here. So anyway, let's discuss the results. So here in this results, this green line is showing for S by D equal to 2, while this solid line is S by D equal to 2. Let's see that green line is for S by D equal to 2, while this black line is for the single file. So you could see in the black line that with the frequency change in the response or dynamic stiffness is not so much. But when you consider spacing between files as a 5, S by D equal to 5 here, and S by D equal to 10, then the difference is, so once you consider this, then this is for S by D equal to 5. So then in that case, the effect of frequency is significant. Because you could see, you could get peak values here. And for this was for S by D equal to 10. But for S by D equal to 5, you get the peak here. So that means when you are increasing the spacing, the first natural frequency or first fundamental frequency of the system is getting reduced, which is shown here. So the peak values which are coming for spacing 5 and 10, they are quite significant, and that will give you a goal. Others, if you leave the peak, then the variation in real part is more or less same, like a linear analysis. Here, the imaginary part, these are the counterpart of the part A, and in this case, what you have, again the color scheme is same. Black is for single file, this is for S by D equal to 2, and then 5 and 10. So this was for about dynamic stiffness at different frequencies, and this work has been already published in Canadian Journal. Listed here. One thing you need to understand, that this whatever we have discussed so far was without structure. Now, if you put on the top of that structure, then the analysis will be solid file structure interaction, not only solid file interaction. In that case, this is SPSI. What is the effect of structure? Before we discuss the structure of structure, let's talk about that. These different curves. What has been presented in this case? This has been presented using what is called the period you have here, which is in seconds, and you have, which is inverse of the frequency, cyclic frequency. And on y-axis, you have amplification with respect to input pattern motion. That means what has been presented, going to be presented, that is a normalized value showing the amplification with respect to input band of motion. That means amplification divided by the input band of motion. So these values ultimately turn out in terms of ratios. So let's try for this, that how it works. So what you have here, the black line is free fill, while this red line is pile head, and then you have blue line pile head with interaction and without interaction. So you have a pile head without interaction and with interaction. So this is with interaction, while you have without interaction also. So this is the value without interaction. Then same thing for structure. The red line is without interaction, while the blue line is considering the interaction. So what you have here? That means one thing is C, that even if you consider SSI, both structure and that soil part, that means you consider the SSI analysis in two ways. One is without considering interaction and another is with interaction. So when you consider without interaction, that is the same thing, considering that your soil column is situated on the back. Okay. So these are the results here. So you could see that when you don't consider the interaction, without, in that case, what happens? That this interaction effect will decrease. So this was without interaction, red line. Okay, here, and the blue was with interaction. So the peak values drastically decrease, and this was for structure. Same thing is for the pile head, response at the pile head. So this was the response without interaction, and this was with interaction. So in general, as we discussed at SSI also, that the interaction effect which you consider decreases the amplification factor of the response of the system. Okay, so this has been also already published in soil direction and earthquake engineering. Thank you very much. And what you have this evaluation of soil parameters in the laboratory, because time is up, so I will quickly. So see that when you carried out the soil pilot structure interaction analysis, or let's say you are carrying out that soil interaction analysis, then you require to calculate the parameters of the soil. And these soil parameters need to be determined in the laboratory. There are two apparatus. One is called cyclic triaxial testing apparatus, which we have at IIT Roorkee. This is able to deal with high strain testing. So if you need to carry out the high strain testing, for example, for liquefaction, then we use this device. But for wave propagation problems and other problems, you require an equipment which can deal with low strain. And for low strain, this is the facility. This is called Vision Column Test apparatus in our laboratory. So this completes, and this was the references for the today's lecture. The first reference is the postdoc report, which I have completed postdoctorate from Washington University in St. Louis, Missouri. So this report or the project work was only on 3-dimensional finite element nonlinear analysis for soil pilot transition that I wrote. So this is available, but already much of this contents of this report has been published in journal publication. Particularly, you can see the ASC's journal of geomechanics, and would also like have Canadian Geotechnical Journal, and then you have soil dynamics and earthquake. Then there is a book by Wolf, which is fundamental book, which we have already discussed. I thank you all. Thank you very much for your kind attention.